What about that fellow? Shumnath?
Shumnath joining question. He is not at it.
He's just got in, like it?
No. Ullo boday wo interested na boday.
Okay, shall I start? Okay. So, very good afternoon or good evening. So, we are going to have the 5th lecture today. 4 lectures are over on solid state NMR. So, I have given some simple examples of silicon-29 mass NMR. Mass stands for magic angle spinning. It is so magic that we can get high resolution NMR from the broad line shapes. Normally, it comes for solids, so you can get high resolution NMR pattern from solids. That is why we call it as a magic angle spinning NMR. This magic angle spinning interaction also we have studied. What are the interactions? One is the chemical shift anisotropy, another is the dipole-dipole coupling, and third one is the quadrupolar interaction. These are the 3 main interactions. Small interactions are there which we are not considering. So these 3 interactions are represented by tensor. So tensor we have different components. Is a second rank tensor. We have 9 components, 3 squared. Second rank means 3 squared, which is nothing but 9 components. So for the time being, we would only discuss about chemical shift anisotropy. So dipolar and quadrupolar, we will discuss it a little bit later. We were discussing what is the origin of phosphorus 31 NMR chemical shift here last class. We discussed SpPO4 and SpOPO4 and how there is a large shift in the chemical shift value. Then we discussed I have just introduced this topic that if you have a pure gallium phosphate and pure aluminium phosphate, you can see there is a difference. The line shape is first of all different. This is relatively broad compared to this one. This is relatively sharp. Chemical shift difference or the line width is smaller here. Line width is slightly larger here because aluminium forms a more covalent bond. So, covalent bonds, more electron densities, their chemical shift anisotropy is more. If in around the phosphorus structural units in aluminium phosphate compared to gallium phosphate, that is why averaging is not that good. Here the averaging is very good. So the moment you replace part of the gallium with aluminium, what you are getting is gallium 80%, aluminium 20%. Similarly, we have gallium 50-50, gallium 50, aluminium 50, gallium 20, aluminium 80. This is just the reverse of this one, and we have aluminium phosphate. So if you systematically see, in fact, you need not go for 0.2, 0.1, 0.2, 0.3, 0.4, 0.5, etc. You systematically see line shape changes. Correct? Na? You see 3 peaks here. Similarly, you also see 3 peaks here. Only thing is its intensities are different. Here, if you see here, it is like a symmetric pattern on central pattern. First two other. This peak, this peak. They have same intensity. This peak, same intensity. This is the maximum intensity. So what we are having is here nothing but this is aluminium gallium phosphate. Let us consider the compound aluminium 0.5, gallium 0.5, PO4. So here 50% aluminium is there and 50% gallium is there. So if you have such type of compound, you are having a phosphorus structural unit with 4 aluminium as near neighbors, and also you are having a phosphorus structural unit with 4 gallium. In addition to that, we have got phosphorus structural unit 1 aluminium, 3 gallium as next near neighbor. Near neighbor is always oxygen. So next near neighbor only important here, because near neighbor always in phosphates, near neighbor is always oxygen. So in this phosphorus, there is 1 aluminium and 3 gallium as near neighbor, next near neighbors. Near neighbors is oxygen only. Here in this middle peak, we have phosphorus structural unit with 2 aluminium, equal number, 2 aluminium and 2 gallium as next near neighbors. These are the 5, 1, 2, 3, 4, 5. 5 phosphorus structural unit present in a 50-50 solid solution. This is a 50-50 solid solution. Why? Because this is 50% aluminium and 50% gallium is there. So this, in fact, one can predict it. How we will predict it? Suppose I gave a solid solution of aluminium 0.1%, gallium 0.9% and phosphate. What will be the NMR pattern? The intensity can be predicted from the simple expression. Probably I will solve one problem today in the class, and then for other composition you have to try at your home, and otherwise I will give as an assignment, so you can try at your home leisurely and you can submit to me. How to calculate, how to predict the intensity pattern for other composition, like for example aluminium 0.1, gallium 0.9. I have not shown here. Similarly, aluminium 0.7, gallium 0.3. What is the pattern, NMR pattern, which I have not shown here. You have to predict it and then you have to submit the assay. Probably today and tomorrow I will give. But tomorrow also there is one more compound I will solve for a slightly different structure so that you will get some idea. So to predict the line shapes, now it is very, very important that the aluminum and gallium should be randomly mixed. If it is not randomly mixed, then there will be segregation. We cannot have this type of pattern. This type of patterns are only possible for a random distribution of aluminum and gallium. So whenever there is a random distribution, how do you know it is random distribution? Just like that you formed the compound doesn't mean that you got a random distribution. If it is a random distribution means we should have a linear variation of lattice parameter. X is nothing but content of either aluminum or gallium. If aluminum is X, gallium is 1 minus X. If gallium is X, aluminum is 1 minus X. As a function of X, if we are getting linear variation in the lattice parameter, then we say it is a random solid solution. And this binomial distribution can be used to predict the NMR pattern. For example, if you like stainless steel or something like that or other alloys, we cannot use it. Only if it forms a random solid solution, then we can use binomial distribution to evaluate the concentration of different structural units, and thereby you can predict how the NMR pattern of a particular solid solution will look like. Okay, let us come back to this solid solution again. Aluminium 1 minus X, gallium X, PO4. PO4 is constant and part of the gallium is, or part of the aluminium is replaced by gallium. Or either you can say part of the gallium is replaced by aluminium or part of the aluminium is replaced by gallium, one and the same only. So in such a system, suppose you take a general formula like aluminium 1 minus X, gallium X, phosphate, how many structural units will be there? There will be 5 structural units, correct now, which I have discussed. One is phosphorus with all 4 aluminium as next near neighbor. Always remember that next near neighbor. First near neighbor is oxygen. Then there will be 3 aluminium and 1 gallium. There will be 2 aluminium, 2 gallium. There will be 1 aluminium, 1 gallium. There will be all gallium. And their relative concentration changes with the composition of the alloy, composition of X. So this is only for a binary compound, not valid for ternary compound. Ternary compound you have to consider it as 2 binary terms, 2 binary components. But we will consider for a simple system like a binary component like this one. There is an expression, relative fraction of an aluminium. Let us forget about aluminium or gallium. We can take either aluminium or gallium. So if you have an aluminium with R gallium as next near neighbors and 4 minus R aluminium as near neighbors, that is why the F stands for here. F stands for fraction of aluminium with R gallium as near neighbors, next near neighbors. Forget about near neighbors because near neighbors are all oxygen only. So fraction of the aluminium structural unit with R gallium as next near neighbors and 4 minus R aluminium as next near neighbors is given by this type of expression. 4Cr into, where X stands for this X. X is nothing but this X, small fraction, into 4 minus R. So 4Cr we can, because NCr, this is the expression, NCr is nothing but n factorial divided by n minus R factorial into R factorial. So this is the typical expression based on the binomial distribution. So let us take a simple system like a 50-50 composition, simple solid solution. You have to solve for other composition. I will just today explain to you how to solve for 50-50, 50% aluminium, 50% gallium. Okay. Now let us take this composition 50-50. So let us have a composition with what is the structure, relative concentration of a structural unit with 3 aluminium and 1 gallium as next near neighbor. What is that? 3 aluminium and 1 gallium. So that is why R is here what? 1 gallium is here. So 4 minus 1, which is nothing but the aluminium. Correct na? R is nothing but 1 gallium. Here we are mentioning about R na, this R. This R is nothing but number of gallium, which is 1 gallium, and 4 minus R is nothing but 3 gallium. So this is nothing but F3, 3 aluminium, 1 gallium as next near neighbors. So this can be easily calculated. If you apply the R is 1, so we know 4 is equal to, instead of aluminium, you can take gallium also and vice versa. Results will be same. So if you substitute in this formula, it will become 4C1 because R is 1 gallium. then X is 0.5. So 4 minus R is nothing but 4 minus 1. And this is 0.5 raised to 1 because R is 1. So 4C1 is nothing but 4 only because 4 factorial. 4C1 is nothing but 4 factorial divided by 4 minus 1 factorial divided by 1 factorial. What is 4 factorial? 4 minus 1 factorial is nothing but 4 only. This you can calculate 4 into 3 into 2 into 1 divided by 3 into 2 into 1 into 1. So only 3 into 1 will cancel. Okay. So 4C1 is nothing but 4 only. I'm sorry. 4C1. You can easily calculate 4. 4 into 3 into 2 into 1 divided by 4 minus 1. 3 into 2 into 1 into 1. So all of them will cancel and you will end up with only 4. So that is what I have shown here. So 4C1 is 4 and 1 minus 0.5 0.5 into 3. So this should become 0.25. So what is 0.25? 0.25 is the relative intensity. Total everything will add to 2 fraction. Fraction of aluminium structural unit with 1 gallium and 3 aluminium as near neighbors. Hope you understood. If you have any clarification or if you have any question, you please stop at this stage. So at any point of time, you can stop. You can stop me. So hope you understood this one. So this way I have calculated the relative fraction of aluminium structural unit with 3 aluminium and 1 gallium as near neighbors. The answer I got is 0.25. Let us. Yeah, you too. Whether somebody has asked question or not, I don't. No, nobody has.
Right, any question at this stage?
Any question at this stage?
If so question you can announce.
Yeah. If you have any questions, please, any questions, clarification or a doubt, please feel free to stop me at this stage. So because simple expression.
One is there in
Concurrent viewers. Okay.
इसमें one है उसमें दो.
Okay. 3 student. Actually, normal. Okay, we will. Anyway, they can mail me also. Any problem is there, they can mail me. Any clarification is there, they can mail me. I will give an assignment on something of this only, a different composition. For example, aluminium 0.1. I am solving this expression for 50-50. That means 50% aluminium, 50% gallium. Mole fraction is 0.5, 0.5. So I got a relative fraction, assuming it's a random mixing of aluminium and gallium. If you take white balls, if you take black balls, if you take aluminium as white balls, if you take gallium as black balls, put it in a each 5 number of aluminium and 5% of gallium, and if you shake it very well, so you can find out how many aluminium will have gallium as near neighbors by this expression. So you can see here fraction of aluminium with 3 aluminium and 1 gallium as near neighbor, which is around 0.25. Hope things are clear to you. Now let me see the other one. Okay. So if you repeat this, I suggest you to repeat this because already I have given you for calculation of 3 aluminium and 1 gallium. So similarly, you can calculate for how much it will be there for 4 aluminium and 0 gallium, because 4 aluminium is there means it is satisfied, 0 gallium. So it is nothing but 4C0 into 0.15, 0.5 into 4 into 0.55, you will get 0.0625. This is nothing but fraction of the phosphorus structural unit with 4 aluminium and 0 gallium as near neighbors. This you remember, it is for a particular composition 50-50, 0.5 gallium and 0.5 aluminium. Similarly, you can calculate, this I have calculated just now, and this you can calculate 4 minus 2, which is nothing but fraction of phosphorus structural unit with 2 aluminium and 2 gallium. So if you substitute 4C2 you can easily calculate 4 into 3 divided by 4 minus 2, 2 into 1 into 1. So it will become, we calculate here also, 4C2 is not 4 into 2, 4 into 3 divided by. So it's just using this expression you can calculate. NCR is nothing but n factorial minus n minus r factorial. So 4C2 is what? 4 factorial divided by 2 factorial into 2 factorial. So 4 factorial divided by 2 factorial into 2 factorial. Correct? Now 2 factorial is nothing but 2 factorial. 2 only. So 4 by 4 it will become 1. So if you calculate like that, what you get is the relative fraction of phosphorus structural unit with 2 aluminium and 2 gallium is nothing but 0.375. Similarly, if you same expression, there is no doubt about it. These are all very straightforward calculations. You can find out the fraction of the phosphorus structural unit with 1 aluminium and 3 gallium. Just a reverse of whatever I have mentioned here. Here it is 3 aluminium and 1 gallium. Here it is 1 aluminium and 3 gallium. That is nothing but 4C3. 4C3 is nothing but 4C1 only. And 4C1 is nothing but 4. If you multiply this, you will get 0.25. So that is why the value is same, 0.25 and 0.25. And if you have 0 aluminium and 4 gallium, you will get this as the fraction. So if you add everything together, what will happen is we will get 1. So this is nothing but the fraction of the 5 different structural units of.
Sudarshan,
Yes, sir.
because this population actually, this is the reason that you are getting symmetric peak, no?
This is the reason that we are getting 5 symmetric peak. For example, if you see the intensity, that will become, this will be 0.25, this will be around 0.375, or this will be this around this one. But this intensity I will show you. This, the most intense peak will have around 0.375 because we are getting like this peak. We are getting like this peak. We are getting like this peak. Am I right? We are 1, 2, 3, 4, 5. These 5 are 5 different structural units. And this is 0.0625, 0.0625. And this is the bottom, next one is 0.25. Sorry, my handwriting is too bad. And this will come here actually.
Well, that's okay.
And the top one is, the middle one is 0.375, 0.375. And the next one is 0.25. And the last one is 0.0625. You can see that, 0.0625. So if the random mixing of aluminum and gallium takes place, and if the composition is 0.5, you can predict a NMR line shape like this one, the middle one, which you are showing. You can see here, whatever you are seeing here, that NMR line shape can be predicted. So this way, you can predict the NMR line shape. I have written the poor handwriting, but remember that this is the way that we can, the total intensity if you add together will become 1.
So let's go back to the previous one. So this one,
Previous one.
yes, this P over L4 and all these things, how those population will be dependent on the fraction of gallium and aluminum.
Whatever gallium, because this concentration is 50-50, 50% gallium equals the symmetry, because equally used, phosphorus use equally,
yes,
aluminium also, gallium also.
So, yes. But when the ratio is different, then how those are distributed?
When the ratio is different, that is why I have shown here, 50-50 is okay, you are getting a very easily. The moment you have a ratio like 80% aluminium and 20% gallium, or whether we are having a ratio like 20% aluminium, 80% gallium, the ratio changes. There also we can use very well this binomial expression and we can get intensity pattern.
That also follows binomial.
Binomial distribution. Why it is binomial distribution? Because we are getting linear variation in the lattice parameter. That means it is randomly mixing. Aluminum and gallium are randomly mixing. Because of this randomly mixing, we get linear variation in the lattice parameter, and in such systems, we can use binomial expression to predict the NMR line shapes. So you can suppose somebody gave you, or suppose you take an XRD of a sample and find out that you are having a linear line shape, then you can predict the NMR line shape. So that is the purpose of showing this example. Of course, this is for a specific system like a spin half nucleus like phosphorus, silicon, or like a phosphorus, silicon, then we have got nitrogen 15 is spin half nucleus. This type of system in nitrates we can predict it. But the moment you go to quadrupole nucleus, prediction becomes impossible because this type of variation or resolved peak, it will be difficult to get because of the line broadening effects. Aluminium phosphate, gallium phosphate is a representative system. It is a basic system we have taken to explain how the chemical shift changes, how the mixing or solid solution can be understood, etc. This is something called the cation distribution in solids. So many times we have a random cation distribution, then properties like thermal expansion coefficient, band gap values, all thermophysical properties or thermal properties get averaged out. You can calculate from the composition. For example, if you have a compound like 50 gallium, 50 aluminium, you can take the average of aluminium phosphate thermal expansion coefficient and the gallium phosphate thermal expansion coefficient and average it. So you will get a value which is close to that of aluminium 0.5, gallium 0.5 PO4. But if there is a non-random mixing, there is sometimes what happens, there can be preferential segregation. Aluminium segregate, gallium segregate. In such cases, it is not possible to say the cation distribution, as well as one cannot predict the properties, thermal expansion coefficient, micro hardness, band gap values, etc. One will not be able to predict. This is a very simple system. I thought I will. So any problem, please feel free to contact me. I am going to give one assignment, and the assignment is like this. You have to calculate for other composition. For example, if I have a composition of aluminium 0.1, gallium 0.9, PO4, which I have not shown NMR pattern, can you predict what will be the typical intensity pattern for phosphorus with all 4 gallium as next near neighbors, with one aluminium and 3 gallium as near neighbors, 2 aluminium, 2 gallium, 3 aluminium, 1 gallium, 4 aluminium as near neighbors. It can easily predicted. You make a table. For example, the samples which I have not shown here, NMR pattern, like 0.1 I have not shown, aluminium 0.1 I have not shown, aluminium 0.4 I have not shown, aluminium 0.9 I have not shown. So if possible, you try to calculate this and submit as an assignment. One more assignment I am applying this. This is easy to calculate. One more assignment I will give you tomorrow. That is also similar lines only. Once you solve this, you will be able to solve that also. So this pattern, again, whatever I have explained only, see, this is the typical mass NMR pattern for 50% aluminium, 50% gallium. It was repeatedly told. I have also shown in the previous NMR. You see the relative intensity pattern you see here. One is 0.0625, 0.25, 0.375, 0.25, 0.0625. So by taking an NMR, and if you show the relative intensities are like this, then we say it's a random solid solution. There's a perfect random mixing of cations. So this type of pattern probably you might have seen 1, 2, this is a pendant. Sometimes proton also gets coupled. If you have 4 proton, it is pendant splitting is there. Then you say 5, 1, 2, 3, 5 signals are there. You can calculate how many number of protons are there. These are belongs to a coefficient called Pascal triangle. Probably in your high school classes or in your 10+2, you might have learned about Pascal's triangle. What is a Pascal triangle? The intensities are coefficients of binomial intensities. For example, if you take this expression, if n is equal to 0, then what happens? We have only 1. This is called binomial expression. If n becomes 2, what happens? We have 2. 1 is to 1. If n becomes 2, what happens? We have this term as well as this term. So if you take it now, it will become, when n is equal to 1 to 1. 1 is to 2 is to 1, it will become. So like that, you can keep on generating. You will form a triangle. You see, you first write 1, then side by side you write 1, 1. Then sum of these 2 and 1 again if you write. Then you take the sum of 1 and 2 and write 3 here, sum of 2 and 1, write 3 here, again write 1. So like that, you can form a Pascal's triangle. One edge will be 1, 1, 1. Another edge will be also 1, 1, 1. But this base edge will be nothing but the intensity pattern. So we have n is this, whatever the value which I have shown here in this case now, corresponding to n is equal to 4. Because we have actually n is equal to 5, we have taken n is equal to 0 also as 1. So here you can say 4 is nothing but it is having a pattern 1, 4, 6, 4, 1. So if you divide this 0.0625 by 0.0625, what you get is 1. Here you will get 1, here you will get 4, and here you will get 6. Here also you will get 4, here also you will get 1. 1, 4, 6, 4, 1. That is what you are getting here. 1, 4, 6, 4, 1. So same thing, this is a Pascal's triangle, which you can say, if you Google in internet, you can say Pascal, you can get the Pascal's triangle. So this is
how you selected this n equal to 4.
Actually, sir, हमारे साथ n is equal to 5. We have n is equal to 5 because 5 structural units are there. But here already taken n is equal to 0 as 1.
Okay.
One intensity. So n is equal to 4, nothing but it corresponds to 5 only effectively. So that is why this pattern 1, 4, 6. If you take a sum of these two and then divide also, you will get this number.
Yeah.
0.0625.
That is there.
That is it. So similarly, if you have in a structural unit with 6 neighbors, 6 structural unit. Now only we have 5 structural unit in this system, in this binary system. So n is equal to 4. So n minus 1 actually we have taken. Number of structural unit minus 1. Suppose you have something about 6 structural units, then we should take phi is equal to 1. So I give an example, maybe this class itself I will give another example. So before going further, I thought I will explain this also. Nowadays, many people tell about core shell nanoparticles. In nanotechnology, many times there are techniques are available, synthesis methods are available. You can make a core and a shell. What is this core shell particles? Core can be one material, shell can be another material. So that is generally called as a core shell particle because core may be different, shell may be different. It can be same also, core can be same, shell also can be same. That is also possible. Or shell is different from core, that is also possible. So now synthesis methods are available in which you can very well make core shell particles. So how you make a core shell particles? The simple chemical methods are available. First you nucleate core. So nucleate core, let us say in our case, core is gallium phosphate. We are explaining lot of NMR results of P31 mass NMR because it is easy to understand and it is easy to spin off nucleus. It is easy to explain the chemical changes around phosphorus. So silicon also something similar to that only, you can explain easily. The moment you go to quadrupole nucleus, then the line shapes gets broadened and it will be slightly difficult. Of course, now methods are available to get narrow line shapes from quadrupole nucleus. So let us say how a core shell particles can be characterized by P31 mass NMR. Normally people characterize core shell nanoparticles by recording TEM, transmission electron microscopy, or atomic force microscopy, or other techniques, or luminescence, etc. But using NMR also, you can characterize a core shell. Our core shell particles you cannot characterize, but some representative core shell particle can be characterized by P31 mass NMR, magic angle spinning NMR. How you prepare a core shell particles? First you make a core. First you take a precursor solution. For example, in our studies, we have taken gallium phosphate as the core. So I take a gallium salt in solution and nucleate and form gallium phosphate by adding a phosphorus precursor, phosphate precursor, not phosphorus precursor, phosphate precursor. So I take a typical concentration of gallium. Procedures are available. I may not discuss in detail. If you are interested, you can mail me. But just for your understanding, I am briefly mentioning the procedure. First to take gallium 3+ solution in aqueous medium, add phosphate precursor. So what will happen? It will form gallium phosphate nucleus. Then you add some ligands. There are different types of ligands. Mainly surfactants are used as ligand. Like you can use oleic acid or you can use SDS. SDS is nothing but sodium dodecyl sulfate. Or there is another common ligand called CTAB, cetyl trimethyl ammonium bromide, etc. These are ligands which come and stabilize the core particles, core nanoparticles. So by using soft chemistry, you have made gallium phosphate nanoparticles stabilized with ligands. Ligands are required, otherwise they aggregate and you get bulk material. Now I will add shell material. What is shell material? Shell material is nothing but aluminium phosphate. So in the already nucleated or already nanoparticle formed system, gallium phosphate nanoparticles are formed in the solution, and to that I add aluminium 3+ and phosphate species. So there are two possibilities. One is homogeneous nucleation in which aluminium phosphate alone will precipitate. In the another case, the heterogeneous nucleation in which aluminium phosphate migrate through the ligand and precipitate on the surface of the gallium phosphate. So two possibilities are there, but in general, heterogeneous nucleation possibilities are higher. This we can confirm by other techniques also. So by this procedure and using suitable concentrations and suitable stabilizing ligand, you can make a gallium phosphate core covered with a aluminium phosphate shell. So this has been confirmed by not even by NMR alone, by other techniques also. There is a gallium phosphate core covered with the aluminium phosphate shell. So if you have a gallium phosphate core, then we have a chemical shift value. You can see here. You see here the chemical shift value is around -10 or -9 ppm. And we have got aluminium phosphate shell, which is coming around -20, 27 ppm. What are these in between peaks? We have a phosphorus structural unit with 1 aluminium 3 gallium as next near neighbor. We have phosphorus structural unit with 2 aluminium 2 gallium as next near neighbor. We have got a phosphorus structural unit with 3 aluminium 1 gallium as next near neighbor. What are these? These are nothing but these are the phosphorus structural unit existing at the interface of core and shell. So there is a core of gallium phosphate which is characterized by a peak at -10 ppm, and we have a shell of aluminium phosphate, pure shell. There is no contamination, there is no dissolution of gallium in aluminium, and there is no dissolution of aluminium in gallium. We have individual peaks which is characteristic of the core and shell, but we have interface peaks, which are characteristic of the phosphorus with 1 aluminium, 3 gallium, which are phosphorus with 2 aluminium, 2 gallium, which are phosphorus with 3 aluminium and 1 gallium. I am just telling you, I am showing you this example mentioning that it is difficult to find by other techniques what will be the nature of the phosphorus structure unit at the interface of core and shell. Of course, shell and core one can distinguish by doing some luminescence or europium, etc. By doping core and shell, you will be able to find out whether it is core europium and shell luminescence. But what is the structural unit at the interface? That will be difficult to say. Phosphorus NMR is an ideal technique to see this. In fact, for some of the silicate nanoparticles also, one can use this method to find out simple by recording one-dimensional P31 mass NMR. You can say how many phosphoruses are there, what are the different types of phosphorus existing at the interface of this core shell nanoparticles. Please feel free to stop me at any stage. This is just so you can understand. Once you understand the phosphorus aluminum NMR shown here and the shift in the chemical shift values, you can always understand what is this phosphorus structural unit, what is the interface, the phosphorus structural unit existing at the interface. So my assignment is this only. Is it possible to calculate the different structural units of phosphorus with varying compositions of solid solution? For example, x is equal to 0.1, 0.2, 0.3, 0.6, 0.7, 0.8, and 0.9. So if possible, is it possible to, is an assignment you take it, maybe you can read at home and you can maybe after 3-4 lectures, before at the end of the lecture, like 12th lecture also, you can submit the assignment. And by using the same analogy which you have used for the calculation of different phosphorus structural units, can you calculate the different structural unit in SnO2 TiX, SN1 minus X TiX or O2 solid solutions? So this is somewhat more involved. I will just give you some hint how to calculate that. Then this you can calculate at your home and then submit as an assignment. These are the two problems which I am giving you as assignments. You can download it also. This slides will be there in the YouTube. You can download it. So I just to give you how to calculate this. Maybe after 1 or 2 slides, I will explain to you how to calculate this, because I am going to finish this phosphorus NMR. So I thought first I will explain about phosphorus NMR, then I will go to the tin NMR. So this can be solved only by recording tin NMR. So this I will explain maybe after 1 or 2 slides. So before going further on this phosphorus NMR, this phosphorus NMR is not only it is very sensitive to the chemical shift values, the chemical shift line shapes also it is very, very important. Just you see here, this is a phosphorus 31 NMR of bismuth phosphate. Bismuth phosphate is a very, very, very interesting molecule or a very, very interesting system phosphate, which has got a lot of application as a luminescent material. Because this bismuth is having an identical shape, identical lattice param, this ionic radius and electronegativity compared to that of lanthanide ions. So lanthanide ions are very good luminescent materials. So you can put lanthanide ions at the place of bismuth and then get the luminescence properties. Why bismuth? Because getting pure quality of lanthanide ions is difficult, because you know lanthanide ions, another terminology is rare earths. They are really rare in the environment. So you have to give a lot of energy, you have to waste a lot of chemicals, etc. to purify lanthanide ions. Particularly if you use different lanthanide ions as a host, then a lot of lanthanide ions is required for their manufacturing luminescent material. So if you use a material like bismuth, which is having identical properties as that of lanthanide ions, it will be advantageous. So that is why a lot of studies are going on in bismuth phosphate based system. So in bismuth phosphate based system, bismuth is having an ionic radii comparable to that of lanthanide ions. Why we study this? Why NMR is relevant for that? Because the bismuth, if you see, bismuth atomic number Z is very, very relatively higher compared to the lanthanide ions. So higher Z means what happened? The electron cloud will be more. Anisotropic created around phosphorus will be higher. So that is why you see the line width of bismuth bismuth phosphate quite high actually. It is of the order, it is ranging from -10 to almost like plus 15, almost like a 25 ppm line width, pure bismuth phosphate. But the moment you start substituting lanthanum, then you can get smaller and smaller line width. You see here smaller and smaller line widths. But one thing you should notice here, we are not able to get a well resolved peak. Like in aluminium phosphate and gallium phosphate, in aluminium phosphate, gallium phosphate, we are able to get different configuration. We are able to get separate speed. Even if this spinning speed is very small, it is around 5 kilohertz. You can see here. Spinning speed is around 5, I have mentioned here, spinning speed is around 5 kilohertz. Even with 5 kilohertz, we are able to distinguish individual phosphorus structural unit. Whereas in this sample, we are spinning at a frequency of 10 kilohertz. I have mentioned here, spinning speed is 10 kilohertz, almost double than that. Even after double spinning speed, you are not able to get well resolved peaks for phosphorus structural units with a different barium and lanthanum as structural units. This is mainly because of the very high asymmetry or the electric field created by the bismuth and lanthanum. So due to this, the line shape is somewhat broader and we are not able to get a well-resolved peak. Probably if you do at a much higher spinning speed, like 10, because in our system or the whatever around us, we can go maximum 15 kilohertz. And if you want to go to higher like 35, 40 or 60, then you can get sharper and sharper line shape, and probably you will be able to distinguish between phosphorus structural unit with a different number of phosphorus and aluminium as next near neighbors. So this is one aspect which I want to convey. But one another problem is there, once you go to higher and higher spinning speed, you will get smaller and smaller rotors samples, which I have shown in the some of the third lecture, I think. So your amount of material becomes smaller and you have to record a long time NMR spectrum. Now you have to record larger number of scans to get a meaningful signal. So since it is having a large value of anisotrope chemical shift component, by using the line shape, there are nowadays programs are available. Probably I will not be discussing how to calculate the line shape or now how to calculate the chemical shift parameters, sigma 11 and sigma 22, etc. Just to have a feeling of these chemical shift anisotropy values. We have calculated the delta 11, delta 22, delta 33, etc. And I have mentioned here. You can see here as bismuth phosphate, you see here sigma 11, sigma 22 are relatively higher magnitude actually if you see here. As you go to lanthanum phosphate, it decreases, it has come minus 26, minus 36 has come minus 26, minus 6 has come minus 5, 27 has come become 18. So the values are relatively lesser. The chemical shift anisotropy or the components of chemical shift values. Component, because I mentioned in the second lecture that the chemical shift anisotropy is nothing but a tensor. That once you have a tensor, it can be converted to diagonal elements if you assume principal axis symmetry. So that is why it will become a diagonal. So we have three components of chemical shift anisotropy. So sigma 11 is nothing but minus delta 11. Sometimes people write sigma 11, sometimes people write delta 11. They are same only. Only thing is there is a charge. Delta 11 is minus sigma or sigma is minus delta 11. You can write. So you can see bismuth phosphate is having a higher anisotropy value, sigma values or delta values as can be seen compared to the LaPO4. That is also reflected in the line shape values. You see here, the averaging effect is better in this case, whereas the averaging effect is poor and you get large line widths in the case of bismuth phosphate compared to the lanthanum phosphate. The purpose of showing this example is that the sigma or nothing but the delta chemical shift anisotropy parameter is directly related to the line width of the NMR pattern. Procedures are available. I think if anybody is interested, I can show you. But I think for the chemist point of view, I think may not be of that significant. So if you are interested, you mail me, I can give you the procedure. So before concluding, this was phosphorus, just to buy phosphorus NMR is ideal to identify, to determine or to monitor the structural units in glassy material, because glassy material are very difficult to get information from X-ray diffraction or Raman spectroscopy or neutron diffraction, etc. Because the primary requirement is that the long range ordering for any crystalline material, because glasses does not have, they have order only up to few angstrom. So that is why we are not able to get good signals from phosphorus NMR, particularly from XRD and neutron diffraction techniques regarding the structural units, whereas NMR can give different type of structure. For example, if there is a structural unit, like you see here, this is a pyrophosphate structural unit. Pyrophosphate means was phosphorus here and another phosphorus here, another oxygen here. Of course, this is pentavalent only. There's a charge is double bond is there. So 2Q1 structure, why Q1? Because there is only one bridging oxygen atom. Remaining 3 are non-bridging oxygen atom. So 2Q1 structural units. That is characteristic of a pyrophosphate structural unit. Whereas a metaphosphate structural unit is having what? We have one Q2 and two Q1 structural units. So in a glass network, whether it is consisting of metaphosphate structural unit or pyrophosphate structural unit can be very well recorded, very well determined by recording the P31 NMR. So this is a typical example in which one can easily interpret. You can see a peak here. You see peak here. This is nothing but the Q1 structural unit of phosphorus, and this is nothing but Q2 structural units of phosphorus. So in this composition, for example, if you take a composition of 40% lead and 60% P2O5, we have mainly Q2 structural units. You see here Q2 structural unit. There is no end member, means it's a circle. See, if you have a long chain, then we should have end member. If you have a chain, we have end member. Correct, na? It's a circular unit, then we need not have a end member. We have only Q2 structural units. The moment you have end member, it's a linear chain. So in this case, for example, if you see 40% PBO containing sample, we have only metaphosphate circular chains of metaphosphate structure. We have only Q2 structural unit. You see here, we have only Q2 structural unit. But the moment you go to 60% lead, we have got Q2 also, we have got Q1 also. That means this type of structural units are predominating. Q1 structural unit is there, Q2 structural unit is there. So one will be able to see, one will be able to predict what type of phosphorus structure, whether it's a Q2 structural unit is predominant. If it is Q2 structural unit is only present, then we don't have end member. It will be like a chain. We don't have end member, because end member means we can only have Q1. Whereas in this, there's a slight Q1 structural unit is coming. You see the Q1 structure. Here it is significantly high. So here mostly circles, and here it is small amount of Q1 structural units are there. This way, one can predict what is the different type of phosphorus structural unit, whether it's a Q2, whether it's a Q1, etc. We can predict from this. What is the use of this? People will ask, why you want to know all these things? Because glass important aspect is optical gap. If you record UV visible optical absorption spectra of glasses, we can get some, we can derive, actually we can get a plot, we can get a similar plot from the UV visible optical absorption spectra of glasses. And from this UV visible optical absorption of glass, we will be able to calculate optical gap. The gap between, actually one should not say valence band and conduction band, the gap between the ground state and excited state you can get. That is called the E optical value. E optical value of the gap glass you can get. And this E optical value of glass strongly depends upon the number of non-bridging oxygen atom and the number of non-bridging oxygen atom. Why bridging? Because if you have a non-bridging oxygen atom, there is negative charge here. Here negative charge is there, here negative charge is there, here negative charge is there. Here negative charge is there, here negative charge is there, here negative charge is there. If you have a bridging oxygen atom, then we do not have a negative charge here. We do not have negative charge here. So if you have a negative charge here, what is the advantage? If you have a negative charge here, then it is easy to excite the electron from the negative charged oxygen, because already negative charge is there, whereas it is difficult to excite the electron, because it is difficult to excite the electron from the bridging oxygen because there is no negative charge. Whereas in non-bridging oxygen atom, there is a negative charge. So the moment there is a negative charge which is delocalized over all this oxygen is there, then it is easy to excite the electron. Whereas here, it is difficult to excite the oxygen electron because this is a bridging oxygen atom. So if we have more and more non-bridging oxygen atom, then the optical gap will decrease. Energy E optical will decrease. The same thing we see here. If you take an optical absorption spectrum and if you plot the absorption coefficient versus wavelength or energy, the curve we get is like this. And if you draw the straight line, you get the E optical values. In fact, E optical value decreases with increase in non-bridging oxygen atom. E optical value decreases. The arrow shows it is decreases with the increase in concentration of non-bridging oxygen atom. For example, if you have 40% lead oxide in the glass, we have an optical gap of around 3.4 electron volt. If you have 60% Pb oxide in the glass, we have got an optical value of, we have got an optical band gap value of 3.2 electron volt. So 3.2 electron volt optical gap is you can easily calculate what is the wavelength corresponding to that. Because in any optical measurement, you require cutoff wavelength or band pass filters or cutoff filters or notch filters, etc. So in such cases, the relative concentration of the non-bridging oxygen is an important parameter. So if you have an idea about that, then you will be able to explain the observed variation in the E optical values. So once you know the E optical values, you can predict the cutoff wavelength or onset wavelength of absorption. And this will be very useful for making the material, different type of material for optical applications. So this is the reason that I have shown this slide, one of the application of NMR in which you can predict what is the relative concentration of bridging and non-bridging oxygen atom. And from this, you get idea regarding the optical gap. So any glass, we can predict what will be the optical gap. Any phosphate or silicate glass, what will be the optical gap, we can predict. This phosphorus NMR is very, very sensitive. Normally in glass, now there are two things. One is called a network former and another is called a network modifier. In this glass, this is the network former and this is the network modifier. Sometimes some oxide, it will act both as a former as well as a modifier. So depending upon the network, if it is acting as a modifier, then it will keep on modify the network and it will keep on creating non-bridging oxygen atom. If it is a forming as a network former, then non-bridging oxygen concentration will not increase. It will form a network. So by monitoring the relative concentration of non-bridging oxygen atoms, you can predict whether it is forming a network or whether it is forming a network former or whether it is forming a network modifier. So here we say we put small amount of THO2 in these glasses to see whether it is acting as a modifier or former. So what we observed is that it is always modifies a network up to some concentration, and after that phosphorus NMR is remaining more or less same, indicating, for example, beyond this, these two B and A, the NMR it is not changing. See this one, A and B sample, there is no change in the phosphorus NMR. Whereas beyond that, there is a change. The Q1 structural unit is increasing, indicating that the network is getting modified. So small amount of THO2 always forms the network, and the moment you increase the concentration of THO2, it modifies the network. Of course, modifying the network is not good for practical application, because once you modify the network, you will get lot of non-bridging oxygen atom, and which result in the degradation of the glass. So the stability of the glass to a certain extent can be predicted with the help of this NMR. Now let us come back to the assignment. So I have told one assignment is this one. Calculate the relative concentrations of gallium about different phosphorus structural unit and predict the NMR pattern of all these compositions. If you have any doubt at any point of time, you can contact me. Now I am giving you one more assignment in which how you can get different structural units of tin, because tin is NMR active. Tin is a spin half nucleus. Tin is NMR active. So how you can get different tin structural unit from a solid solution of SN1 minus X TiXO2. So I don't want all the composition, I want only three compositions. One is X is equal to 0.25, another is X is equal to 0.5, and another is X is equal to 0.75. So just to give you some clue how to do the calculation in the next few slides. Because this problem you will be able to solve only if you understand the structure of tin oxide. So here, instead of phosphorus NMR, we will do tin NMR. Tin, one of the NMR active nucleus is tin 190. So this is the typical unit cell of tin, SNO2. SNO2 is also known by the name called the cassiterite. Cassiterite structure is same only, this only. Here, we have a tin here at the center, which is called the body center. Body center of the tetragon, we have a tin. This is the tetragon. Why tetragon? A and B are same. C is not equal to same. Correct, na? C is A and B are A not equal to B. B and C are same actually, nearly same. So here A is here, C is here, and B is here. I have drawn here. Here the atom is at the center. This is called a tin atom. Blue colored atom is tin atom. and there is one oxygen here, one oxygen here, one oxygen here, one oxygen here, one oxygen. So how many are there? 4 are there on this surface, correct? Na? On this plane, and another 2 are there. One above, we can say these oxygens are called apical oxygens, apical, and these are called in plane. 1, 2, 3, 4. These are called planes in plane. In plane, we can also call as equatorial. Equatorial or in plane, same only 1, 2, 3, 4. These are called equatorial oxygen, whereas these are called axial oxygens. Axial oxygens and equatorial oxygen, their bond lengths are different. You see here, one is very small, only different, but it's a different 0.206 nanometer with 2.06 angstrom, and another is 2.05 angstrom. Had it been same, then we would have told that it's a perfect octahedron. Correct? Na? Perfect octahedron is nothing but a cubic system. Cubic symmetry is there. So we will get a very sharp line shape. Chemical anisotropy will be very small. But it is not a perfect octahedron. It is a distorted system. Tin oxide is a distorted octahedron. Now, this is called the near neighbor. We have 6 near neighbor. Now let us come, what are the next near neighbor? 6 oxygens are the near neighbors. Where are the next near neighbors? We have 1, 2, 3, 4. 4 next near neighbors. Similarly, 1, 2, 3, 4. 4 next near neighbors with almost equal distance. But we have another next near neighbor here, which is slightly away. Slightly away this plane. There is a plane above plane and there is a below plane. There is one atom. One tin atom here, one tin atom here. So how many next near neighbors are there? Next near neighbors are 10. Why? Because 1, 2, 3, 4. 4 from here, one apical oxygen here, which is very much away from the center tin. Then 4 here, 1 here, 5. Similarly, 4 here, 1 here, 5 total. So 5 above and 5 below. You forget about below, 5 left hand side, 5 right hand side. If you take a vertical tetragon, we can say it is 5 above, 5 below. Since if you consider as a horizontal, 5 tin above left side and 5 tin right side. So there are 10 tin as next near neighbors. That is what I have written here. 10 tin as next near neighbor. Next near neighbor is next near neighbor. N. Near neighbor means only 2 N's. 6 oxygen as near neighbors and 10 tin as next near neighbors, and their distance is different. Why?
Because Darshan,
Yes, sir. Yes, sir.
This site tin atom,
Center tin.
that is actually center tin. Right now,
Huh.
that center tin above this plane or above this box, below that box, one tin atom
Can be there, but they are away. They are not considered as a near neighbor. First, for near neighbor, we consider which is the closest and what is the next closest.
Okay.
These are away, again higher than that. It is around 0.4 nanometer or something. Roughly.
Okay, that will be far away.
Too far away. And will be applicable for the above unit cell. Above, there is one unit cell is there. For that, it will be applicable actually. So if you see the near neighbor distances, we have 6 oxygen and we have a next near neighbor of 10 tin. 2 or 8 are at the plane and 1 above, one left hand side and 1 right hand side, much more above, much more at a farther distance. So how many configurations of tin can be possible if you make SnO2 TiO2 solid solution? If I make SnO2, I think this was one of the my question. If I make a SnO2 TiO2 solution, if you compare with aluminium gallium phosphate solution, 10 tin as near neighbors. So we have 11 configurations. Why 11? Because in the case of aluminium phosphate, we have got 5. Even though 4 aluminium only as near neighbors, we have 2 end members. So total 5 configurations will be there. Since we have 10 tin as next near neighbor, we have 11 such configurations. Correct now, we have 11 such configurations possible in the case of an SnO2 TiO2 system. I think, let us, if you take a 0.5% tin, Ti 0.5, we have 50% tin, 50% titanium, we have got 11 such configurations, 11 peaks we can get. And if it is forming a random binomial distribution, if it is a random mixing, we will be able to explain how many tin will have 1 titanium as near neighbors, 2 titanium as near neighbors, 3 titanium as near neighbors, etc. This problem probably you have to do. I will help you to do this. And tin is why I want to tell is that I will just give you some more information regarding SnO2. SnO2 is having an octahedral configuration and isotropy, chemical shift anisotropy is quite high. Why will chemical shift anisotropy is quite high? Because it's a distorted octahedra. And it won't length or not, because tetrahedron, had it been a cubic system and had it been a perfect octahedron, then we would have got a very small asymmetry and we get, but it is slightly distorted. So that is why we get a spectrum like this one. This is the typical tin NMR spectra. You see here, there is an isotropic peak. These are called side bands. Origin of sideband I have discussed in the last class. Probably we will, I will indicate you maybe in the next class. But sideband intensities can change depending upon the spinning speed. And this is the only isotropic peak. And this line width also show, this sideband pattern also show that there is a, if you take a static pattern, you will get a very, very broad line shape. Because this is one of the components of the chemical shift anisotropy, sigma 11, sigma 22, sigma 33. So average effect of these two peaks will be coming as sigma 33, and this will sigma 11 will be somewhat close to that, and sigma 22 is somewhat something like this. So this pattern also show that the tin environment is highly distorted with the chemical shift or the anisotropy values around minus 557, minus 575, and minus 678. Always you see 633 will be highly shielded compared to sigma 11. This has been calculated, the sigma values has been calculated based on a program. So this available standard, I think you may be able to get it from also the Google and all this free software may be available. From the sideband patterns, you can get the intensity. So one can definitely say there is a significant chemical shift anisotropy exists in this pattern. So now let us assignment anyway you have, and I hope you might have understood. You can interact with me in the next class also regarding the assignment. Probably you can submit it towards the end of the course. I think I will go to next class, I think, correct? Now already 4:35. I will close it. Please feel free to contact me, or you can stop me at any time. You can now also, you can, if you have any queries or any clarification, you can stop me now also. So anybody is having any doubt, please feel free to mail me also or write to me. Sorry, I think it started a little late, so I thought I. Any queries, any doubt, you can cross.
So how much time to take in the question in the chat box?
Okay. Question. Okay. Sir, how much time it takes doing a P31 mass NMR? P31 mass NMR will not take much time. Suppose you have a like aluminium gallium phosphate or gallium phosphate, within 10 minutes you can finish this P31 mass NMR. But before that you have to set the magic angle, etc. Magic angle setting may take around 10 minutes. And the recording will not take much time. Maybe 10 minutes, maybe 8 to 10 minutes it will take. We can get a good NMR pattern from by recording mass NMR signal for 10 minutes. But for silicon, etc., it will take maybe 2 hours, 3 hours, etc. But for phosphorus, because it is also 100% abundant, phosphorus 31 nucleus, so we can quickly measure. Thank you. Thank you for the question. Any more questions?
No, then.
Okay, if there is no, I am going to close the lecture. Thank you very much for attending the lecture. Please come Friday, next Friday. Today, I think day after tomorrow.
Yeah.
Next one.
At 3:30.
At 3:30, please be there. Thank you very much. And good evening.